Kia ora koutou, Reese from QuickSense here, and today we're looking at circle symmetry and specifically chords. Now this question here is asking the relationship between the angle at AOB, which is this angle in here, and the angle ACB, which is this angle in here. So what's the relationship between these two things? Well, what we have are two angles which are subtended, so the word is subtended, by this chord. Well, there's a chord here, and there's a chord here, right? So, the way we're going to look at this is by thinking of it in terms of the inscribed angle theorem, right? And if you want to do a little bit of extra work, you can think about why this theorem works. So I've got A over here, okay, and we're thinking about the relationship between this angle at the top and this angle down here. And you'll notice that in this instance, we've got two chords. So the inscribed angle theorem says that the angle BAC is half of the angle. So the other angle is, so BAC is, let's get that D, BDA. So two lots of this first angle are the same as this bigger angle BDA. So what does that mean for our question here? Well, the relationship, if you think about moving C along the outside of the circle, you'll see there's a connection here between the inscribed angle theorem and our subtended angle. So if we move it around, then we can see that ACB moves up there, and we have an equivalence here now, right? So ACB is half of AOB. The angle ACB is equal to half of the angle AOB. All right, this next question here is a classic geometry problem solver, where you're given a lot of information and you're going to have to work backwards to get to what they're looking for. In this instance, what they want to know is the value of M, and M is down in here. And so what I'm going to begin with is for looking at certain symmetries and certain important points about the diagram. A really important point here is that AC and BC are tangents. Okay, so AC and BC are tangents. Now what does this mean? Well, this means that this angle here and this angle here, those are right angles. Okay, they're right angles, that's what we mean by tangent. It's where the line meets at a right angle at some point, A and B. And what else do we know? Well, looking at this, I can see that ACB, right here, is similar to the question we had before, where we have our inscribed angle theorem, right? I've got this shape going on here, where this angle is 55, and then this angle is two lots of whatever this angle is. So this angle, ACB, is equal to 2 times 55, which is 110 degrees. with that in mind, what else can I use? Well, I can use the fact that the shape ACBO is a quadrilateral. It's a kite. And the interior angles of a kite, or any quadrilateral, are equal to 360 degrees. So, if OAC is 90, ACB is 110, and 90 here, then what's this going to be? Well, that AOB is equal to 360, take away, well, what have we got? We've got 90 and 90 and 110. Right, so that's 360, take away 180 to 90, 70 degrees. Okay, if that's 70 degrees, then this angle here, right, this angle EOB, angles on a straight line, okay, 180, take away 70. That's angles on a straight line. Okay. So to back up a moment, this angle here is coming in there and there. Yeah? Then we've got EOB equaling 110 again. And notice we've got this nice little relationship, yeah, between this angle and this angle here. I wonder what's going on there. The last thing we need to figure out is M. I know this value here, and I can also see that this is the radius and this is the radius. Therefore, we've got an isosceles triangle. M is equal, so OEB is equal to OBE. Okay, so if they're the same, then 180, this is angles in a triangle, so M times 2 plus 110 equals 180. 180 take away 110 is 70, which is equal to 2m. 70 divided by 2 is equal to 35. So m is equal to 35 degrees.